Okay, let's get started here. So basically, what is the Bode plot? It was introduced by S.W. Bode, wherein frequencies were varied from omega is equal to 0 to infinity. So when you are varying frequencies from omega is equal to 0 to infinity, there is a wide range of variation. To accommodate this variation, what he does is that he utilizes a logarithmic scale, so it becomes very easy. Now, if you look at omega is equal to 1, so log of one value will give you infinity. In calculator, it will give you math error. So, magnitude as well as its phase, or if any transfer function is given, its magnitude as well as its phase, when it is plotted against logarithmic values of frequency, it gives you the complete picture. Magnitude as well as phase when it is accommodated in one single plot, that is called as a Bode plot. Now, when you are changing the magnitude, like for example, any transfer function is given. So g of s, h of s, you just have to put it into frequency domain. Put the value of s as j omega. And now in Bode plot, we will use dB. So what does dB mean? If you are going to multiply anything with 20 log to the base 10, that means into x, this would mean x dB. Okay. So let's suppose 20 log to the base 10. Okay. So this is x is equal to 10. Okay. That is one decade. So 20 log to the base 10 into 10 would give you 20 dB. Okay. Now the most important concept here is to understand what is a decade. Okay. In the Bode plot, I told you it cannot start from omega is equal to 1. Okay. It can start before it because omega is equal to 1 will give you infinity. So, or omega is equal to 0. Sorry, because 20 log 0 will give you infinity value. So the Bode plot starts from a lower value 0.01 or at times in the question 0.1. If you see from 0.01, okay, the movement is 0.02 up to 0.09 to zero point 0.1. So this is one decade here. Same way from 1 to 10 there is a decade. One, sorry, 0.01 to 1 there is a decade. 1 to 10 there is a decade. Right, 10 to 100 there is a decade. 100 to 1000 there would be a fourth decade there. So as I've already mentioned, log 0 is equal to infinity. In calculator, if you put log 0, it will give you a math error because it can't compute it. Now, let's move further. How to calculate the decades? Suppose you had a frequency here at omega is equal to 0.01 and another frequency, let's say omega is equal to 8. Now, you need to see how many decades are there in between them. If you carefully analyze, there is one decade here, right? Then one more decade here. Then there is not a complete decade here. Okay, so 2 plus 2 decades are confirmed, right? 2 decades are confirmed. And this decade, this point we need to calculate. Now, how do we go about this? So, number of decades would be equal to log to the base 10 omega 2 by omega 1, right? This is the formula. Okay, number of decades is equal to number of decades would be equal to log to the base 10, okay, whichever value omega n by omega m. Okay, this is the basic formula. Let's say omega 2 was equal to 8 and omega 1 was equal to 0.0. So you'll do log to the base 10 in calculator. Normally log to the base 10 is given as a log function, and if you have a log to the base e which is not utilized here, that is given as ln. This is just for your understanding. So log 8 to the base 0.01 would be log 8. Now you don't have specifically log 800. How do we calculate this? So you can just use this log 8 plus, okay, log to the base 2. So log to the base 2 would be 2 log to the base 100, right? You can utilize these formulas. Log ab is equal to log a plus log b, and same way this x to the base n, same formula I have utilized here. So what I get, log 8 value I get, so 2.903 dBs is a shift. Okay, so if you can see, there is a 2 full decade shift here and there is a zero point 0.9 dB shift over there. Now also note this change in dB would also be given. If you are noting the change in dB, this formula we will be utilizing later will be equal to slope into decades. Now the main advantage of using the logarithmic representation is that it converts the multiplication, division, into addition and subtraction. Now normal open loop transfer function, if you notice here, is given in this form. S of z is equal to k, s plus z1, s plus z2, sp. Now notice here, either s of z would be present or s of p would be present. Now why is the case? Suppose your z value is 3 and p value is equal to 2, right? So that means s of 3 by s square. So this will reduce now. Only s is left. Okay. If it was vice versa, s square by s cube, it would have been 1 by s. If both are s and s, none of them would be present over there. So this is a standard question that would be given in the examination. But now this question you need to convert into time constant. In order to convert this into time constant form, what we need is the Bode plot needs to be evaluated and it needs to be written in the time constant form. In order to get into the time constant form, what you do that s by z, s plus z1 was there, take the z1 out. So once you are taking the z1 out, what you are doing actually is this coefficient of right z1 should be 1. This should be 1. This p1 should be 1, p2 should be 1. We need to remove this in time constant form. So it will give you a result 1 plus s by z1, 1 plus s by z2. Same way p1 you take out, p2 you take out. Now once you take out p1, p2, you are left with this z1, z2, p1 and p2. So this is called as k effective into k, right? So this is called as k effective into k. So that would be k into z1 into z2, p1 into p2. This is your k effective. So k effective value is this, okay? This is your k effective value, wherein k value is this. And now basically 1 by z1 is given as t1, 1 by z2 t2, 1 by p1 t and tb. So finally you arrive at a time constant form in the Bode plot. So the Bode plot will give you a representation of this in the time constant form. Whereas your k effective is nothing but k into, right? If you are having two, if you just have one pole, 1 0, so it would be only z1, right? And let's say two poles, so it would be p1 into p2. Or let's say vice versa. If you are having only one, let's say uh, two zeros, then it would be k into z1 into z2. And let's say you have one pole, okay, then it would be just p1. Same way, okay. So p is basically the time of the system, and these are the time constant forms. Now, very important way to understand is basically what does a pole do? Pole basically adds minus 20 dB to the slope. Okay, what does a zero do? Zero adds plus 20 dB to the slope, plus 20 dB to the slope. Now you see, we have gotten it into the time constant form wherein I have written k effective value over here. So let's say you are having g of s, h of s as k. So how do you get the magnitude of it? Magnitude would be under root k square by k. So now in the dB value, it would be 20 log to the base 10 k, right? This is its dB value. Okay. Now 20 log to the base k I have written. If I give k value greater than 1, okay. So if you give 20 log 1.2, right? So you just check 20 log 1.2 value. 20 log 1.2 value is equal to 1.58. 1.58. But if it is less than zero point 0.1, let's say k is zero point 0.9. So 20 log zero point 0.9 will give you a value minus, right? If k is less than 1, so it is giving you minus 0.915 dB. Suppose this is 0 dB. Okay. If the k value is greater than 1, so the resultant magnitude would be always above the 0 dB line. If k is less than 1, it would be downwards. This is the meaning. So whenever you are making a Bode plot, your x-axis is the logarithmic axis which the semi-log sheet takes care of itself. Whereas at the y-axis, okay, you have to multiply. You need to get the magnitude in dBs. So whatever the magnitude, you have to multiply it with 20 log to the base 10. Okay. As far as the angle is concerned, it would be same 30 degrees like this. So you see the y-axis is a linear axis, whereas your x-axis is non-linear axis here. Now the important conclusion here is that how to get the phase of it. Like for example, k plus 0, so it would be tan inverse. So phase for k is 0, okay. But what about minus k? Minus k, the phase won't be 0 degrees. How do you get minus k? Minus k you get by multiplying c k at an angle theta. If you want 1 minus 1 into k at an angle theta, right? Like this. So 1 at an angle theta is given as cos theta plus j sin theta. Now if you put theta is equal to 180 degree, right? Or let's suppose theta is equal to minus 180 degrees if you, okay. So you will get cos of minus 180 is as good as cos of 80. 180, because cos is an even function. Cos of minus theta is equal to cos theta, whereas sine of minus theta is not equal to sine theta, it is equal to minus sine theta. Anyways, whether it is minus or plus, it hardly matters here, because sine n pi is 0. That means sine 180 is 0, right? Even if you are multiplying minus by 0, it will become 0. So this function is only possible if your k value is negative. That means your phase would be equal to 180 degrees. Okay. So this is the meaning, minus 180 degrees. If k is negative, it contributes minus in 180 degrees, independent of any frequency over there. Now we will see how the pole added minus 20 dB. The pole is basically the denominator function. So put s is equal to j omega 1 by j omega, and contribution due to the pole is 1 by omega. Now you need to convert this 1 by omega into the dB form. So you just write 20 log g omega 1 omega 20 log 1 by omega. That is 20 log omega minus 1. Here you can just use the formula na, log x to the power n is equal to n log x, right? So here you notice the n value is equal to minus 1, correct? So you can write this as minus 1 into 20 log omega. So this is similar to the equation y is equal to mx. That is one pole at the origin. Now you see it is contributing to 20 dBs, right? Suppose because 10 to the base 10, so it would be equal to minus 20 dBs. Similarly, if you have n number of poles, right? Like let's say k by minus 20 log dB, if you have n number of poles, like 1 to the power omega p times, the contribution due to it would be 20 log omega minus p. So the contribution is minus p into 20, right? Into log omega. So if you have two poles at origin, it is going to two poles being two, it is contributing your minus 40 dBs. Three poles will contribute minus 60 degrees. So basically the poles are contributing angle depending upon the number of poles. Now in general I have written the formula this over here, minus 20 into. Similarly, like for the zeros, if you notice, the angle contribution would be plus 20 dB, because 0 is upscale only. Now 0 would be like this: g of s h of s is equal to s only, right? So you just putting the j omega over there, okay, and the magnitude of it is omega only, so you just have 20 log omega, right? Which is, if you put to the base 10 10, so this is 20 dB. If you have 20 log omega to the power p, it is contributing p into 20. Okay. Now as far as the phase angle is concerned, like 1 by s, you are putting, so 1 by j contributes minus 90 degrees. Similarly, if you are seeing 1 by sp, 1 by j omega p, so this contributes basically 1 by minus 90 into p. So like if you are having two poles, so it will contribute minus 180 degree. Three poles, it will contribute one at an angle of minus 270 degrees. Okay. So now what are the steps basically to draw the Bode plot? Now first step you have to do is express the given expression into time constant form, right? You need to calculate the value of k effective, okay, which was equal to k, right? The number of poles z1 into z2, it depends upon the zeros and the poles, p1 into p2 first, and then you have to do this 1 by s by z1, right? 1 by s by z2, same way 1 by p plus 1 by s by p1, right? 1 by s p2. So this 1 by p1 is ta, and 1 by p2 you already know is equal to tb. Okay. Now draw a line of a 20 log kb. First, whatever the value of k is there, if k would be equal to positive, most of the cases which we need, so you have a 0 dB line over here. Okay. Just take 1 centimeter is equal to 20 dBs. Draw this as 20 dB over here, and below 0 dB the line will be minus 20 dB. Now if you have to draw 20 log, suppose it is log 6, right? So if you just put in the calculator 20 log 6, so you'll get an answer of 15.56, right? So 15.56 dB. So you need to draw this line first. This line would be constant throughout, right? Now shift, then what you have to do is that once you have drawn this, okay, 20 log, draw a line appropriate slope, basically representing poles at zeros at the origin. The first thing is that we have to see what to see. Either we can have poles or we can have zeros. Normally we are having poles. Okay, so we have to see at the point here, this is your omega value. Yeah? Omega is equal to 1 corresponds to your 0 dB. It intersects here, right? So what you have to do, draw a line of appropriate slope representing poles or zeros. Now the slope here, right? The initial slope will be contributed due to the number of poles. Suppose there are two poles at origin or one pole at origin. So initial slope starts from this minus 20 dB, this minus 20 dB. A slope minus 20 dB is falling slope, right? This is falling. From 20, it is going down. A rising slope is plus 20 dB. This contribution is due to the poles. This contribution is due to the zeros, right? Hmm? Then shift this intersection point on the 20 log K line. Wherever this is, see, the 20 log K line is this. 20 log K. You have to shift this intersection point there. So this results in addition of constant K and number of poles or zeros at the origin. Now the important point is that you have to change the slope at various corner frequencies for poles minus 20 dB and for so corner frequencies, like for example, if you are given the transfer function, let's say I have a transfer function. This is I have considered this as you have two poles at origin. Okay, let two poles at origin means 1 by s square. At omega is equal to 5 one pole. So that means this term s plus 5. Okay. At omega is equal to 10, there is one zero. So that would mean s plus 10. Zero is coming in the numerator, right? And at omega is equal to 25 one pole. So that would give you s plus 25. Okay. This is the contribution of this pole. Now the corner frequencies are associated with this. This 10, this 5, and this 25. Okay. These are your basically the frequencies that are associated. Now only possible if this is already expressed in the time constant form. This equation already I am having in time constant form. So that means, so s square is contributing what? Minus 40 dB, right? Because two poles. If it was s cube, contribution would have been minus 60 dB, right? Now at s is equal to 5, what is the contribution? It is again a pole, right? So, so we will go from the lower value. Omega is equal to 5. So now you have to start, right? So 0.01, let's say, to, let's say omega is equal to 5 or zero point 0.1. Some cases zero point 0.1. It depends what is given in the graph. Okay, if it is zero point 0.1 to omega is equal to 5, my slope is minus 40 dB. Okay, now at 5, the slope changes again by minus 20 dB, right? If I go beyond 5, my slope would be the previous slope minus 40 dB plus the present slope. So the slope would be minus 60 dB. Till where the slope would be minus 60 dB, the slope will remain minus 60 dB till 10. Now at 10, I am having a 0. At 0, my slope addition would be plus 20 dB. So the previous slope was minus 60. Now the resultant slope would be minus 60 dB plus 20 dB. So here I have a 40 dB minus 40 dB slope, right? At 25, what I am having a pole. So the contribution here is how much? Minus 20 dB due to the pole. Now the resultant pole beyond 25 up to infinity, because there is no other corner frequency, minus 40 minus, so it would be minus 60 dB. So you have to understand how to evaluate these poles and the zeros. Okay. So some important terms regarding the Bode plot is the gain crossover frequency. What does it mean? Basically, the gain crossover frequency, if you can look there, the frequency at which the magnitude of this is unity is called the gain crossover frequency. So this is only possible when your omega value is 1. So then only the magnitude would be 0 dB. So I have already, it can be defined at which magnitude of GGO is unity. Omega is 1. That is 20 log to the base 10. Okay. And omega is equal to 1, 0 dB. So we can say that frequency at which the magnitude of this is equal to 0 dB. Now it's called the gain. Now phase crossover frequency, the frequency at which the phase angle contribution would be minus 180 dB is called the phase crossover frequency. Now let's go to the gain margin. Now what is gain margin basically? Now gain margin is basically how much margin I have to increase the gain before the system becomes unstable. Okay. So gain margin does not discuss about the present stability of the system. It is about how close you are to the disaster, how close you are to the instability. So see, instability will happen when basically your magnitude is close to 1. Okay, because your log 1 will become 0, right? 0 dB. Behind it, if you see log zero point 0.9, it won't know, it will be below the 0 dB margin. And phase angle is minus 180 degrees. So gain margin, basically when you have to calculate the gain margin, it is measured at the phase crossover frequency. Whenever your magnitude plot intersects with the phase crossover frequency, that is actually your gain margin. So only thing deciding stability in this case would be your magnitude. Okay, for positive gain margin, the magnitude should be less than 1, right? Because you're 20 log of, and for the negative gain margin, the magnitude should be, okay. So if it is the magnitude of this omega pc, okay, omega pc, if it is less than 1, right? So then you have a positive gain margin. Hmm? But if it is equal to 1, so the magnitude plot, basically, if you notice over here, let's go to the next section. That means how much gain we need to reach before we reach the limit of the stability. So we need to increase the gain until the magnitude reaches the value of omega is equal to 1, beyond which it will become unstable. So that required gain is basically positive. Positive gain margin is margin to reach 0 dB. Same way, okay, then this corresponds to basically below 0 dB. If you are reaching from below, right? If you are reaching from, I'll explain you here. If this is your 0 dB, right? And you have to reach, in order to reach this 0 dB, okay? If the value of, if omega value is, let's say, zero point 0.9, so 20, let's say zero point 0.2, okay? So if you just put 20 log zero point 0.2, the value would be minus 13.9 dB, okay? Now the margin from minus 13.9 to reach omega is equal to 1. This margin is called the gain margin, right? And this is positive gain margin to reach over here. Because see, already it is at minus 180 degrees. This gain margin is positive gain margin. But if your omega was equal to, let's say, 4, so 20 log 4. So if you do 20 log 4, the value you will get is 12. So it's 12. Now you have to decrease this to reach 0 dB. So this is, if decrease, this is the increase, right? So this is negative gain margin. So magnitude is, see, basically in, so the conclusion is gain margin tells us how far the magnitude at minus 180 degree phases from 0 dB. So below the, if it is below 0 dB, then we say it is a positive gain margin. If it is above 0 dB, then we say it's a negative gain margin. Now about the mathematical calculation of the gain margin. So let's say basically our magnitude plot is this. This g omega pc is zero point 0.2. Okay. Now what we need this to be equal to 1. Okay. So in order to equal to 1, what I do is this equation I write. I say this k, wherein k represents your gain margin. How much I have to multiply this zero point 0.2 so that my omega gc becomes 1, right? This equation I've written. So my gain margin can be also written as gain margin, okay, can be, this is the formula for it, 1 by gj omega uh, hj omega. But one condition is that it should be equal, omega should be equal to omega pc, that is equal to minus 180 degree. So this is the formula for the gain margin, okay. Now let's move to the phase margin, okay. So if you want to express the same thing in decibels, then you have to just do it by 20 log 1 by this thing. Okay. So this will be minus 1, right? This would be 20 log, just like in the previous case I've explained, gj omega, hj omega, okay, to the power minus 1. So this becomes minus 20 log this. Now, phase margin, basically, the formula for the phase margin is 180 plus angle at gj omega, hj omega. Okay. Now, phase margin occurs at the gain crossover frequency. That means the frequency at which, okay, your magnitude plot crosses the 0 dB line. The magnitude plot crosses the 0 dB line. is called as the gain crossover frequency. And this gain crossover frequency, when it hits your phase angle plot at that condition, if it is hitting it above minus 180 degree, then we say it is a positive gain margin. And if it is hitting it below minus 180 degree, then we say it is a negative gain margin. So in phase margin, when magnitude is already 1, how much more phase lag can be tolerated before reaching minus 180 degree? Now the condition here is that in the previous gain margin condition, the condition was that phase was always minus 180 degree, right? But the magnitude was not equal to 1, right? What is the condition of instability? Both the magnitude is 1 and phase is minus 180. In order to calculate the gain margin, our magnitude, we are approximating it equal to 1, whereas the phase is minus 180 degree. Now, in order to calculate the phase margin, magnitude we say is at 1, right? So, we are looking for the instability, the disaster position here. What is the disaster position? The disaster position is verge of instability happens when your magnitude is 1 and your phase angle is minus 180, right? So, like gain margin checks how far the gain is from 1, same way phase margin checks how far it is from minus 180 degree. So, in order to see that how far it is from 180 degree, suppose you have a phase angle of minus 5 degrees here. So, how far 135 is there? So, this is minus 180 degree minus of minus 135, which gives you a minus 45 degree. Okay. So, phase margin is basically 180 degree minus the magnitude of omega GPC. Now you see, notice that the phase angle would be always in negative. So magnitude of this would be equal to minus of angle of this thing. That's why you are putting here this minus angle. So it is 180 minus of minus angle of omega G omega PC. Hence your phase margin would be always equal to 180 degree plus angle of G J omega PC. Okay. Now how to identify? Okay, like the stability condition. So this is your magnitude plot, right? You have drawn a Bode plot, and this is the magnitude of GH omega. This is in dB that you have, and this is your phase angle. Okay, this is the phase angle plot. This phase angle you will get by calculation of the phase angle from the equations. This in the next class also I will be explaining you. So now you notice here, okay, now this magnitude plot is crossing the 0 dB line here. So wherever it is crossing the 0 dB line, the frequency down there associated with it is called as the gain crossover frequency. So gain crossover frequency is responsible for your phase margin. And this gain crossover frequency is hitting hit here, right? So it is hitting the phase plot here, the first plot. So it is hitting the phase plot above minus 180 degree, right? It is hitting above minus 180. Now your phase angle plot is this, right? Now the phase angle plot is crossing minus 180 degree line at A, right? So when it is crossing minus 180 degree line at A, whenever it crosses the 180 degree line, the frequency associated with it is called as the phase crossover. So it is crossing the phase there, right? Crossover. And see, it is crossing the 0 dB line, gain crossover. Now the phase crossover frequency will determine your gain margin. Now the phase crossover, if you are extending it, it is cutting the gain margin. The first shot it is taking it here. So it is cutting it below the 0 dB line. So this is your 0 dB line. So I told you the gain margin would be positive when the phase crossover frequency cuts it below the 0 dB line. So this is the condition for stability. Now you notice here your phase crossover frequency is greater than greater than your gain crossover frequency. Your gain crossover frequency, correct? Crossover frequency, and both omega gc uh, is sorry, both gain margin is positive because it is below 0 dB line, right? And phase margin is cutting above minus 180, above minus 180, hence we say it is positive. So this system is stable. Okay. Now unconditional system would be your when your phase crossover frequency. Okay, here you just check your phase crossover frequency is less than, right? Just remember phase crossover frequency greater than gain, then it is your Stable system. Phase crossover frequency less than gain crossover frequency less than gain crossover then it is unstable. Crossover frequency, then it is unstable. Now here you notice that what is happening here. Hmm? This is your phase crossover frequency, right? Phase crossover frequency is hitting the magnitude plot above 0 dB line. So this is above 0 dB, right? Above 0 dB, so gain margin is negative, right? Now notice here your gain crossover frequency. Here the gain is crossing minus 180. Sorry, your 0 dB, the magnitude plot is crossing the 0 dB line here at this point, and this 0 dB line is hitting your magnitude, your phase angle plot at this angle, right? At C. So you see this cut is below 0 dB line. Is below 0 dB line means negative phase margin. So both see omega PC has to be lesser than omega GC. Okay, one condition, and both gain margin and phase margin are less. Now, if both the gain margin and phase margin are equal, then in that scenario, and they are equal to, now here you see both gain margin is zero, phase margin is zero. Why? Because there is no margin. They are cutting at one single point. This is called as marginally stable system. So these things keep in mind. Now we will be solving gate problems for the next class, because this lecture is very important. Okay. Do you know how we got this?